A hypothesis test for a proportion is a test of whether the population success rate in a binomial experiment matches some specific value or matches the success rate in another population. For example, consider giving a medication for lowering blood pressure to a random sample of 60 participants and finding after a month that 22 of the participants had higher blood pressure and 38 had lower blood pressure. Although the majority of the participants in this sample did have lower blood pressure, this is a random sample, and so this result could simply be due to random chance. If the medication has no effect, the expected result is that after a month, half of the population will have a lower blood pressure and half will have higher blood pressure simply due to random day-to-day fluctuations. So the null hypothesis is a success rate p of 0.5. The alternative hypothesis is that p is not 0.5. The process of doing the hypothesis test in this example works much like the process for doing other hypothesis tests. Start with a null hypothesis, compute a p-value, and then interpret the p-value. The p-value is computed by choosing a test statistic and comparing the value of that statistic for the sample with the sampling distribution of the statistic. In this example, the sampling distribution of the success rate x under the null hypothesis is a binomial distribution with n equals 60 trials and success rate p equals 0.5. As described when computing a confidence interval for a proportion, the normal distribution is a good approximation for the binomial distribution if the number of successes and the number of failures are both at least 10. In this example, the number of successes is 38 and the number of failures is 22, so those conditions are met. The most common test statistic to use here is the sample proportion p hat minus the null hypothesis proportion p0 divided by the standard error SE of the sampling distribution of this statistic. The standard error SE is calculated using a formula seen earlier that gives SE in terms of the sample size n and the population proportion under the null hypothesis. And those values can then be inserted into the formula to get a value for the test statistic z. This test statistic is a common choice because the sampling distribution is a standard normal distribution, which is widely tabulated or can be calculated using a computer. The p-value is the probability in the tails of the distribution beyond the sample test statistic, which can be computed using the cumulative density function of the standard normal distribution. The p-value here is about 3.9%, so using a significance level of 5%, the interpretation of the p-value is to reject the null hypothesis, indicating a statistically significant success rate for the medication. A similar test can be done for the difference of proportions between two separate populations. For example, consider comparing the effectiveness of two treatments for high blood pressure by giving the treatments to two different groups of individuals and observing the success rates in each group, with success defined as lowered blood pressure. In this example, the success rate is 22 out of 40 for the 40 individuals who received the first treatment and 27 out of 60 for the 60 individuals who received the second treatment. The null hypothesis is that the two treatments are equally effective, or equivalently that the difference between the population proportions is 0. The null hypothesis population proportion is unknown, but is well estimated as the total number of successes in both samples divided by the total number of individuals in both samples. The test statistic is the difference between the sample means minus the difference under the null hypothesis, which is 0, divided by the standard error SE. The formula for SE is the same formula as the formula used earlier in the discussion of confidence intervals, and those values can then be used to get a value for the test statistic. The p-value is calculated again as before using the cumulative density function CDF and the standard normal distribution. The p-value in this example is about 32.7%, which is relatively large, but p-values this large are certainly not uncommon. The conclusion when the p-value is large is to fail to reject the null hypothesis, so the difference between these samples is not big enough to conclude that there is a difference between the two treatments.